All right, good morning. Welcome back to Calculus 2. So we have a last problem here of the integral test. Again, the three conditions we have to make are that n sub zero and a sub n's are greater than zero. It's a decreasing function and it's continuous. So there, since n starts at one, we don't have any zeros on the bottom. We don't have any negative numbers that we're going to be plugging in here. This is going to work for all of my positive n's. I mean, it's not continuous because we're doing with n's, not x's, but there's no holes and there's no discontinuities in here. So if this was x's, this would be continuous. Again, for x greater than or equal to one. Uh, so are we all positive? We're taking square roots. All square roots are going to be positive, so we're going to be able to do that. So check and check as far as these guys go. And that's all you have to do is kind of hand wave this, like just kind of take a note. Like since, n squared plus one is greater than zero, the square root of n squared plus one is also greater than zero. We check that off. Okay, so we can go ahead and make that claim. Continuous n squared plus one is a continuous function. One over this continuous for all n greater than or equal to one, which check, we have that. Okay. Is it decreasing? So here is my f of x. We're going to go ahead and say, here's f of x, and we'll change our n's into x's so it's continuous for real. And that way we can actually take a derivative because you can't take a derivative with discrete functions. You have to do continuous. So we'll go ahead and we'll change this to saying this is x squared plus one raised to the negative one half power. Okay. And then we'll say that's our f of x. Okay, and then the first thing I'm going to do is take a derivative. So f prime of x is going to equal uh, negative one half, let's see, x squared plus one raised to the negative three halves times my 2x, right? Because you have to do your chain rule. And now the twos are going to cancel, so we're going to end up with a negative x over, let's see, we'll just write this as x squared plus one raised to the three halves power. Again, this is inside of a square root. It's always going to be positive. We have a negative outside of a square, outside of positive and positive. Again, n is x is greater than or equal to one. So this is going to be positive. This is going to be positive. We have a negative sign out front. It's always going to be negative. It's a decreasing function. Okay. Now, this problem, you could probably solve this in other ways, which is fine. But the instructions on this one specifically say use the integral test to show. Okay. So what we have to do is we have to go ahead and take our integral of 1 over, again, I'll leave it as an x squared because we want to take a continuous function here, dx. All right. Okay. So there is no u substitution for this one because if I set my u to be this piece here, there's no corresponding u upstairs. Okay. There might be some other fancy shenanigans I could try to pull with like let x squared plus one be inside the square root, try it that way. So we could try like u is equal to say the square root of x squared plus one, and then say u squared is equal to x squared plus one and try something with this. Again, there's we're gonna have to pull some fancy shenanigans here, but there's nothing here that I can match with without like a lot of fanciness. Maybe there's another way. And the other way is this is a square root inside of a square. This reminds me of Pythagorean's theorem. This reminds me of a triangle. So if I go ahead and go back to our triangular integrations here, and it's a plus, right? So if I have a squared plus b squared is equal to c squared, there's a plus in here. So we're going to go ahead and set the sides equal to my x or my 1. Let's go ahead and do that. So I went ahead and set my x over to the opposite side of my 1 at the adjacent. This is going to be the square root of x squared plus 1. So we're going to be able to do this. Again, you want to set this up so that your sine, your secant is something you can express as a theta. There's nothing wrong with cosine or cosecant, except that when you do a cosine, you have negatives in your dx or du. With your secant, it's fine, but cosecant has negative signs in there. I don't remember my cosecant derivatives as much as I remember my secants. So the reason why I want to set it up this way is because we can say sine of theta is equal to opposite over hypotenuse. Actually, I don't want to do opposite over hypotenuse at all because that's going to be terrible. I want to do tangent of theta is equal to opposite over adjacent. So I have x is equal to tangent of theta. Can't remember doing these. My dx is equal to derivative of tangent is equal to secant squared theta d theta. All right. So here's what we're going to do here. 1 over X squared plus 1 over x squared plus 1. This is going to be adjacent over hypotenuse. That reminds me of a cosine. So we have integral of the cosine. That's the 1 over x squared plus 1. And then my dx, of course, is secant squared theta d theta. Well, okay, one of my cosines cancels out with one of my secants. Okay, that's how those trig functions work. So we actually end up with this guy cancels with this one. So we just have the integral of secant theta d theta. Now we have to remember, like, what was the integral of secant? I know you can remember. So this is going to be the natural log of secant theta plus tangent theta. Right? That's how that goes. We could put this in absolute values. But since we're going to restrict our thetas to being in the first quadrant, we're not going to have to worry about this too much. Okay, so plus C to make it all kosher. Now we can go back to what's going on here. We have to go back to my actual values for x. Secant is equal to the square root of x squared plus 1. So we have natural log of x squared plus 1. That's my secant. Okay, and then my tangent is just x over 1, so plus x. Okay, one of the things we do have is x has to be greater than or equal to 1 because n was greater than or equal to 1. Do I need the absolute values once I know that x is always going to be positive? Not so much. Okay, so we don't really need the absolute values in here. And we go back and say, well, what was my summation, right? We go back to this. We're going to go ahead and say n is equal to 1 to infinity, natural log of the square root of x squared plus 1 plus x. Okay, go ahead and figure that out. Now we have to apply our limits. So as n goes off to infinity, we could say let m equal the limit as n goes off to infinity and go ahead and evaluate what's going to happen here. So we have the natural log of the square root of m squared plus 1, okay, plus m as inside of our natural log. As we are taking our limit here, it's taking our n goes off to infinity, then this is going to go off to infinity plus another infinity. And we take the natural log of the infinity, like, no, this thing diverges. Okay. Okay, so the limit goes off to infinity. This limit diverges. And then there you go. We have a divergent series here. Okay. Again, I know there's other ways you could have done this. There's other limits you could have taken. You can kind of compare it to 1 over x, 1 over the square root of x squared. Okay, which kind of looks like a harmonic series, right? One summation of 1 over x, which we know diverges. So that kind of verifies our thoughts about like this thing diverges. If I tried it another way, would we diverge? Yes. If we tried another test, it would still diverge. So that's always a good thing to be able to do. See, yeah, but specifically on this problem, you must do integral test in order to prove divergence or convergence, because that's what the problem instructions ask you to do. And I'm doing that because, hey, we're going to have a final exam coming up. And do you remember how to do this? And it's a good time to remind yourself how to do it. So thank you very much for watching the video. I'm going to go ahead and say I'll stop here. I'll see you in the next video. And thank you very much. Okay, good. Take care until then.